Cyclical molecules occur when you take a hydrocarbon chain and bend it so that the end carbons react and bond together, creating a ring. Because a new CC bond is formed, cyclical hydrocarbons will always have 2 less H's than the original alkane, alkene, or alkyne. To name these, you follow the appropriate alkane, alkene, or alkyne rules. Now, the ring, though, is always your main chain. You add cyclo in front of the root to indicate that there is a ring. When you're doing position numbers, you can start numbering C's anywhere in the ring and either move clockwise or counterclockwise to get the lowest possible numbers. If there is a double or a triple bond present, one of them has to be between C1 and C2, so that restricts which way you count. Here are some examples. My parent chain for molecule A is going to be my ring of 4 carbons. Because there's 4 carbons there, my root is going to be bute. Now, I do have a double bond and a methyl group attached here. So, that double bond has to be between carbon 1 and carbon 2. Now, if I make this carbon 1 and this carbon 2, my methyl group will be on carbon number 4. But if I go the opposite way and make this carbon 1 and go clockwise, my methyl group will be on carbon 3, which will give me lower numbers. So this will be a bute 1-ene. It is a ring, so I'm going to stick cyclo in front to indicate that. And I'm going to have a methyl group on carbon number 3. So molecule A is 3-methyl-cyclobute-1-ene. For molecule B, my main chain becomes this ring of 6 carbons. Because it's 6 carbons, it's going to be a hex. They're all single bonded, so ane, and because they are in a ring, I put cyclo out in front. That leaves these side chains left to describe. Now, because I have methyl groups and an ethyl group, they need to be listed in alphabetical order. And because I'm in a ring, I can be creative with my numbering. I can make the carbon that's attached to the ethyl group carbon 1 and go around this way to get really low numbers for my groups and to have the numbers ascending in my name, which is always nice. So, deal with the methyls first. I'm going to have 2 methyls, so I need a di in front. They are going to be found on carbon number 2 and carbon number 4. And then I have a ethyl group on carbon number 1. So molecule B is 1-ethyl 2,4-dimethyl cyclohexane. Write the name for molecule C. Pause the video until you have that written. Here's the answer for molecule C. My main chain is the ring of 5 carbons. Because it's 5, it's going to be a pent. And I have 2 double bonds that I need to take care of. The best way to number and get the lowest possible numbers is by making this one carbon 1 and going counterclockwise. That makes one of my double bonds between carbon 1 and carbon number 2 gives me a lower number for my second double bond and the lowest possible number for my methyl group. So this gives me a pent 1,3-diene. Now, because it's a ring, I need a cyclo out in front. And now I just need to describe this methyl group on carbon number 2. So my name is 2-methylcyclopent-1,3-diene. And properties of cyclical compounds. Now, for melting point, when you bend that straight chain into a ring, it makes your molecule less flexible. You can't have bond rotation around the carbon's single bonds. So because of this added rigidity, you can pack them better. So it makes the atoms not wiggle around as much, so they stay in the crystal lattice better. So this increases the melting point compared to the same chemical in a straight chain. Now, bending the molecule and bonding it so that it's in a ring does not make it polar. So because they are nonpolar, they are only attracted to water with weak dipole-induced dipole, therefore they have low solubilities. Other information about cyclical compounds: some of them are used as fuels, some of them are used as solvents for dissolving both polar and nonpolar things, and then also too they are starting materials for building other molecules. A lot of drugs and antibiotics and things like that have ring structures, so if you're going to synthesize that in the lab, you would use a cyclical compound as a starting material. The aromatic family all have rings with resonance in them. So they have 1.5 bonds between each carbon in the ring. Because of this resonance, these rings are significantly more stable than a regular cyclical hydrocarbon. Aromatics were originally thought to have alternating single and double bonds around the ring, so they're sometimes still drawn this way. My ChemSketch program does this. The 1.5 bonds are now shown as single bonds in a ring with a circle on the inside showing the delocalized electrons that are being shared between the carbons. The simplest aromatic is benzene, so it's a 6-carbon ring. Now, when we're doing expanded molecular formulas, we take the ring and simplify it as a C6H6. Or if there's something attached to the benzene, we would write C6H5 and then continue on. Naming aromatics. You follow the cyclical alkane rules, and the benzene is usually your main chain, and benzene is used as the root. However, if the benzene is attached to a chain with 7 or more carbons, the benzene is considered a side chain and it's called a phenyl group. So here are 2 examples showing this. So I would look, and here's my benzene here. 6 carbons in a ring, alternating single and double bonds. That leaves me with 2 side chains, a propyl group and an ethyl group. Now, because eth comes before prop in the alphabet, I'm going to number my carbons 1, 2, 3, 4. And it doesn't matter if you go clockwise or counterclockwise. You'll get 1 and 4 for the positions of your group. Now, my main chain is a benzene. Now, attached to my benzene, On carbon number 4, I have a propyl. And on carbon number 2, I have an ethyl. So molecule A is 2-ethyl-4-propyl-benzene. Now for molecule B. My benzene is attached to a very long side chain, and it has 1, 2, 3, 4, 5, 6, 7, 8. So because my side chain has more carbons in it, then my benzene becomes a side chain, and we call it a phenyl group. So highlighted in red is my main chain. Now for numbering, I will get a lower number if I start from this end, because I have two side chains. I have a methyl and I have a phenyl group. So if I go from this direction, I will have groups on 3 and 5 instead of 4 and 6. So if I have 8 carbons, my root is going to be an oct. They're all single bonds, so ane is my suffix. Now methyl comes before phenyl in the alphabet, so I'm going to do my phenyl first. It is on carbon number 5, and then at the beginning of my name I'm going to have a methyl on carbon number 3. So my name is 3-methyl-5-phenyl-octane. For properties, because we have that ring structure, just like a cyclical alkane, that makes the molecule less flexible. So it has about the same melting point as a cyclical alkane. Which means it's higher than an alkane. Now, having a resonance structure around the ring does not make the aromatic polar. So water attracts it with weak dipole-induced dipole. Therefore, aromatics have low solubility. Now, other things you need to know about aromatics: they often have strong odors, which is where the name aromatic came from. They are used as solvents, they're used as preservatives, and they're used as pesticides.